Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to our channel. My name is Mr. Hassan and the channel you're watching is Malim Hassan.
Chapter 1: Atomic Structure and the Periodic Table. Previously, we said that all things in the world are made of tiny indivisible particles called atoms. Most things have more than one kind of atoms in them, but this piece of pure gold contains only gold atoms. So we call it an element, a pure substance made up of one kind of atom. Zooming back out, we see the atoms become a lump of gold again. Because there are 92 kinds of atoms, there must be 92 elements too, one for each kind. In reality, however, there are close to 120 known elements, out of which the 92 occur naturally. The rest can be synthesized in the lab. In this chapter, we will look at the basic structure of an atom, and then how the different elements are orderly arranged in what we call a periodic table. Although no one has yet found a way to get a close-up view of an atom, different experiments have made it possible to build up a picture or model of what atoms consist of. The colors in this model are of course used to simply distinguish between different particles. In the center of an atom is the nucleus. This is made up of even smaller or subatomic particles called protons and neutrons. The protons each carry a positive electrical charge. The neutrons are as heavy as the protons but carry no charge. This means that overall the nucleus is positively charged, and orbiting around it are negatively charged particles called electrons. The size of the negative charge carried by an electron is equal to the positive charge carried by the proton. Now the electrons are moving at incredible speed, in fact 3/4 the speed of light. So what stops them from shooting off in any direction? If we could pull an atom apart into its components, we'd say that a neutral atom has the same number of electrons as protons, and it is the force of attraction between the positive and negative charges that prevent the electrons escaping. Each kind of atom is identified by the number of protons and electrons it has. A hydrogen atom has just one proton and one electron. An oxygen atom has 8 protons and 8 electrons. An iron atom has 26 protons and 26 electrons. Now, atomic number and mass number. When you look at the periodic table, you will see that each element has its own box, and within that box you will find two numbers: the atomic number or the proton number and the mass number. Taking an arbitrary element X, the atomic number has symbol Z. This number tells us how many protons are in one atom of an element. The number is always the same for all atoms of a particular element. Atoms of different elements have different atomic numbers, meaning they have different number of protons. For example, an atom of hydrogen has an atomic number of 1 because it has 1 proton. An atom of oxygen has atomic number 8 because it has 8 protons. The other number is the mass number. It has a symbol A. The mass number gives the sum of protons and neutrons that are in one atom of an element. A proton and a neutron each has a mass of 1, and the electrons are so small their masses do not need to be considered. And so if we know the mass number of an element and we know the atomic number, we can calculate the number of neutrons of that element. The mass number is equal to atomic number plus the number of neutrons. The atomic number is just the number of protons. Therefore, mass number is equal to protons plus neutrons. If we take oxygen, it has mass number 16 and has an atomic number 8. How many neutrons does it have? Mass number is equal to protons plus neutrons. So neutrons is equal to mass number minus protons. That is 16 minus 8, which is equal to 8. Oxygen therefore has 8 neutrons. Lithium has mass number 7 and has atomic number 3. How many neutrons does it have? Mass number is equal to protons plus neutrons. Thus, neutrons is equal to mass number minus protons. That is 7 minus 3, which is 4. And so lithium has 4 neutrons. And so in summary, the atomic number is the number of protons in an atom of an element, and the mass number is the sum of protons and neutrons in an atom of an element. Energy levels and electron configuration. Electrons occupying the same energy level have approximately the same amount of energy. For the purpose of this video, we shall have the atom in 2 dimensions. We know the nucleus is at the center of an atom and it's made up of protons and neutrons, and around it are the electrons. We also know that in a neutral atom, the number of electrons always equal to the number of protons. So in a neutral atom of carbon, there are 6 protons, which means there must be 6 electrons. The electrons in an atom are organized around the nucleus in different energy levels or shells. Each shell can hold a certain maximum number of electrons. The first innermost shell can hold a maximum of 2 electrons. The other shells can hold up to a maximum of 8 electrons. For example, lithium has 3 protons, therefore it has 3 electrons. The first 2 electrons are in the first shell, close to the nucleus, and the third electron is placed in the second energy shell. This is called a dot and cross diagram and is used to show the electron configuration of atoms. You need be able to draw these diagrams as well as write the electron configuration. For lithium, it will be Li2,1. In the diagram, the nucleus is represented by the element symbol or a black dot. The energy levels are represented by circles around the nucleus, and the electrons are represented by dots or crosses. Carbon has 6 protons, therefore it has 6 electrons. The first 2 electrons are placed in the first energy shell, and the other 4 are placed in the second shell. This is written as C2,4. Magnesium has 12 protons, therefore it has 12 electrons. The first 2 electrons are in the first shell. The next 8 are placed in the second shell, and the last 2 are placed in the third shell. This is written as Mg282. The organization of these energy levels is what gives the elements different reactivities. It forms the basis of arrangement of elements into a periodic table that we'll look at next. And so to recap, each energy level has a maximum number of electrons it can hold. The first energy level is filled first and can hold 2 electrons maximum, and the levels after this can hold up to 8 electrons. The periodic table. The periodic table is this chart with a strange shape, with letters and numbers, neither squares nor rectangles. You may know what some of these letters represent. C is the chemical symbol for carbon. O is the chemical symbol for oxygen. The chemical symbol for iron is Fe. Zn is zinc. Sodium is represented by Na because it comes from the Latin natrium. The symbol for gold is Au because in Latin it was called auros. You will also recognize the numbers appearing next to the letters. For example, the atomic number, which is the number of positive and negative charges of an atom. The distribution of elements in rows and columns of the periodic table is not random or just a matter of design. The position of an element on the periodic table tells us something about its chemical and physical properties and helps us predict how 2 elements can combine. The periodic table organizes elements from smallest to largest according to its core and the distribution of electrons. In the first column of the periodic table, we have elements that have a single electron in the outermost energy level. And in the last column, we have those that have a fully filled outer level. That's why each chemical element in the periodic table has a well-defined neighborhood. Above and below it are elements with the same distribution of electrons and very similar properties. And on its right, it has an element that has 1 electron and 1 proton more and therefore has different properties. We call it periodic because in this table the elements become similar again periodically. Look, if we start with 3 lithium, the properties will vary regularly along the row until 10 neon. There, the last shell gets full of electrons. Then we move to the next row in the first column. The properties of this element 11, sodium, are again identical to the element above it, and so on. In the periodic table, the columns are called groups. Elements in the same group have the same number of electrons in the outermost energy levels. Groups are numbered using the Roman numerals 1, 2, 3 up to 8. Elements in a group show similarities in their physical and chemical properties. The rows are called periods. Elements in the same period have the same number of energy levels. Periods are numbered using the Arabic numerals 1, 2, 3 up to 7. Elements in a period display continuous variation in physical and chemical properties. Relative atomic mass. An atom is too tiny to be weighed by any instrument. A more practical way to determine the mass of an atom is by comparing its mass with the mass of a standard element. In modern scale, carbon-12 is used as the standard element. Relative atomic mass of an element is the number of times the mass of the atom is greater than 1/12 the mass of a carbon-12 atom. The relative atomic mass of a carbon-12 atom is 12. For example, a magnesium atom is 24 times greater than 1/12 the mass of a carbon-12 atom. Then, the relative atomic mass of magnesium is 24. Relative atomic mass is a ratio of two quantities and therefore has no units. Relative molecular mass can also be determined through comparison with carbon-12 atom. Relative molecular mass of a substance is the number of times the molecule is greater than 1/12 the mass of carbon-12 atom. For example, carbon-4 oxide molecule is 44 times greater than 1/12 the mass of a carbon-12 atom. Then, the relative molecular mass of carbon-4 oxide is 44. The relative molecular mass for a molecule can be calculated using the molecular formula of the substance and the relative atomic mass of each element in the molecule. For example, in carbon-4 oxide, the relative molecular mass can be calculated by adding up all the masses or the relative atomic masses in the carbon-4 oxide molecule. Therefore, the relative molecular mass of carbon-4 oxide is 44. For ionic compounds, the term relative formula mass is used in place of relative molecular mass. Relative formula mass of an ionic compound is the number of times the compound is greater than 1/12 the mass of a carbon-12 atom. The method used to determine the relative formula mass is similar to the one used to determine the relative molecular mass of substances. That is, sum up all the relative atomic masses of all the elements in the ionic compound. For instance, relative formula mass of magnesium oxide is 40. Relative formula mass of aluminum chloride is 133.5. Relative isotopic mass. The relative isotopic mass is the mass of an element in relation to carbon-12. The reason why this is the isotopic mass is because some elements have different isotopic forms. For example, chlorine can be found as chlorine-35 and chlorine-37. The isotopic mass is not the number that appears on the periodic table. The number seen on the table is the relative atomic mass. The relative atomic mass of an element is the average mass of the naturally occurring isotopes of the elements relative to the mass of an atom of carbon-12. On the periodic table, it is the same number as the mass number. In basic terms, it is the average mass of the isotopic forms of the element. While we think of this, we must remember that the isotopic forms have different values in their abundance on Earth. For example, let's look at the isotopic forms of chlorine. Some chlorine atoms have mass 35 and some of them have mass 37. In simple cases, you will take both values, add them together and find the average. In this case, it would be 35 plus 37 divided by 2 and you get an average of 36. But this is not how you calculate the relative atomic mass. We need to remember that we are talking about the number of atoms. There are certain number of chlorine atoms with mass 35 and certain number with mass 37. However, within a sample, the numbers of each isotopes are not equal. So we take this into account when calculating the relative atomic mass so that we calculate a weighted average. Naturally occurring chlorine is made up of 75% chlorine 35 and 25% chlorine 37. So say we had a random sorted atoms of chlorine, we would have 75 atoms of chlorine 35 and 25 atoms of chlorine 37. We thus find the total mass of the sample. We do this by multiplying the mass of each atom by the number of atoms present for each isotope. Then we add them together. Chlorine 35 has 75 atoms and chlorine 37 has 25 atoms. So the mass of 100 atoms will be 75 times 35 plus 25 times 37, which gives us 3,550. The mass of one atom will be the total mass divided by the total number of atoms. So the mass of one atom of chlorine will be 3,550 divided by 100, which gives us 35.5. The relative atomic mass has a value close to 35 because there are more atoms of chlorine 35 than chlorine 37. It is a weighted average. An example: lithium has two isotopes with mass numbers 6 and 7. If the relative atomic mass of lithium is 6.94, determine the percentage abundance of each isotope. Solution: total abundance is equal to 100%. Assuming the percentage abundance of lithium-6 is X%, then the percentage abundance of lithium-7 will be 100 minus X%. And then we proceed as we did with chlorine and equate that to 6.94, the relative atomic mass or the weighted average. X times 6 plus 7 times 100 minus X divided by 100 is equal to 6.94. Cross multiplication: 6x plus 700 minus 7x is equal to 694. Minus x is equal to minus 6, x is equal to 6. So the relative atomic mass of lithium-6 is 6%, which means that of lithium-7 is 94%.